Alrighty. So last minute here, live for AOC Day 20 with 5 minutes to spare. So today there won't be any warm up, but I have something else in mind. Um, After yesterday, I started working on this doc here. So I've been reflecting this doc called Am I Being Stupid? And I'm placing in here like a checklist for me to go over of all the things that have caused me to spend too much time when it's a simple fix. Um, and I still need to go back through all my past times and flesh this out, but this covers a lot of them. Correct input day was getting me just yesterday, I think, on my like 2017 day one warm up, where it's an easy problem, and I was debugging the one liner that was surely correct, and of course it was correct. I just didn't have the right input. You added some more to my list. Oh, in the Discord? Great. Well, you would know, wouldn't you? Let's see. Forgot the coffee. Overslept. Swapped X and Y. Yes, excellent. Fortunately, I don't think I've had a problem with swapping X and Y. And the point area grid library has helped with that. Sleeping? Honestly, uh, did you sleep? Is a good one. So I don't have the problem of oversleeping necessarily, but similar. A lot of these, I think I can chalk up to just being tired. Um, let's look for a day this year with a pretty high delta. I mean, I have a lot of high deltas, but geez, day 12? What happened day 12? Hmm. Oh, okay, this one's a little bit deeper. As I meandered, it took me a while before I decided to try. Actually, once I decided to try looking for corners instead of sides, it went pretty fast. Maybe I'll add something here. Discard a good idea. That is something I've done often, where like while I'm talking about a problem, I might mention a good idea and then never revisit it. Right? I get so stuck on the bad idea. Okay, there's our 2 minute timer. Hey Arrow, thanks for the lurk. So I'll try to remember my good ideas if I have them. But I don't know. Maybe focusing on this checklist is even better in a warm up. Maybe it'll help me tonight. But I do. This is something I want to go like more in depth and straight up review all my recordings, and I want to make in depth videos about these. And if I make those videos this year, next year can be a test of that. Like, do I understand these enough to avoid my mistakes? And there's also just being rusty, not recognizing things quickly. Yes, didn't see the DP. You know what? I didn't say DP, but I did say memo. Should you memo? Which is DP, but just top down. Oh, and but I said it. I said it early in the night. I said I will do DP, or like I'll memorize this as a way to optimize. And I forgot I was going to try memorizing it to optimize. I got stuck in a rut, thinking, oh, this should be so, I don't know. So It's on that list. Should you memo? Okay, 10 seconds. Good luck, everyone. Yep, day 20. Okay, race condition. Oh, and we gotta get our input. 20, 24, 20. All right. Another grid. Okay, start and end race condition. Map of a racetrack. Okay. Start and end in walls. Right when a program runs to the racetrack. Left, down, up, right. 1 picosecond each. All right. Programs are allowed to cheat. Rules for cheating are very strict. Exactly once during a race, a program may disable collisions for up to 2 picoseconds. Pass through walls as if they were regular track. Okay, so our state is positioned, and have they cheated yet? Okay. Oh, I think I did Dijkstra a couple of days ago, and then I turned it into BFS, so I have it uncommitted. But we can do this from scratch. So Val, let's do case class state equals position and cheated. No, let's enum cheat case. So we have cheated is our last state. Can cheat, cheating, and cheated. All right. And we can just define our search here. Well, let's see. Let's parse the start and end. Import AOC dot area point direction. Okay. Now let's see. Val start equals input dot. Oh wait, we need our area. Oh, area. Area for input grid. Let's see. Dot to vector. Here we go. We'll just call this the maze, or we'll call it the grid. All right. Area from the grid. So area dot points iterator dot find grid of that point equals start. Okay. Now end similar. Let's turn on Copilot. We can autocomplete this, or not. I guess Copilot that's not fast enough. And then the walls. So we don't even need to worry about out of bounds since the walls wrap everything. Actually, maybe you do. Yeah. Okay, def inbounds. So area contains P and not walls P. There we go. There we go. So now we do our search. Okay, let me make sure I understand the problem. Disable collisions to pass through walls. Okay. Okay. And let's see, inbounds actually needs a cheat state. Yeah. Okay, we'll keep that in mind to do consider cheat. Physics needs more quick sort, never the case. Okay. So we want an int. So this is a Dijkstra. So we want our priority queue and map. Now we'll call this a start pause specifically, and end pause. Okay. So start and cheat, not can cheat. We'll define a next here. Def our next states. Okay, so there's the non-cheating states. And how do we do this? We just take our position, so pause dot adjacent, and then we're going to filter inbounds. Maybe we don't use this inbounds method. Maybe that's not helpful here. We'll just, okay, so we're going to filter, so diff walls, and then we always filter inbounds or area dot contains. And then, yeah, a new map state with the same cheat. Okay. And of course, if cheating, it must stay that way. So if cheating needs its own branch. Maybe we use the match. So cheat match. Okay. And maybe non-cheating can be a method here. But if we are currently cheating, we must use a cheating version. So def non-cheating next. And this one's super straightforward. So list of state. Let's make it a set because I think we start with a set. Yeah. Great. So def cheating next. We only filter area contains, and then we have to progress the cheating from whatever it is. So we need a next def next. This match. So can cheat goes to cheating, cheating goes to cheated, cheated should error out. So cheat dot next. There we go. Oh no, we don't put that there. We don't put that there. We go cheat dot next. Okay. So if we've already cheated, then we do non-cheating next. It's going to return a set of state. If we're currently cheating, we have to return cheating next. It's funny only hearing cheating from the lurk. And if we can cheat, then we have both the non-cheating next and the cheating next. So you need those. Okay. we have what we need. So we have our start state. We need our cost. A map from state to int. Start goes to 0. Okay. And then priority queue. Um, no. We want a priority queue just of the states. Ordering by cost. Not reverse. There we go. Okay. Visiting equals start. This could be a var. While visiting pause is not equal to end. Then we do visiting dot next. And we're going to add a filter here on cost. So dot diff cost dot key set for each s. And we can queue. Yep, that's a typical deal. And then we just return cost visiting. Okay. Val adds 1 equals search. I think I've got this. Oh, and pause. This felt really straightforward. It seems to be evaluating an infinite loop. That's way too long. Perhaps one of these managed to go out of bounds. Well, okay, even in the cheating, we filter area.contains. I guess we'll have to print some states and see where our bug is. Comment that out for now. We have non-cheating, we have cheating. And if we can cheat, we can choose to cheat. Cheating next, not cheating next. Okay, it's probably somewhere in our Dijkstra. So we start at start, right? We get the next. The key set will always be the min cost, or the min cost will always have the minimum. So we do want to filter that out, right? We don't want to override it. So cost of visiting +1, of course, and then q.enqueue. Oh, wait, we forgot to set visiting to something else. Visiting equals q.dequeue. There we go. No element to remove from the heap. Okay, so we got into a situation here. Well, at what point does that happen? So let's print all of our visiting states. So this goes on for a while. We just never find the end. Here's an end state. We can try it out on the example. Let's try the example. 2024, day 20.text. Save that. Okay. 03 cheating. 12 can't cheat. I'm tempted to turn this into an A star bit. I want to figure out why. So visiting that positive line, why the queue is running dry. So what happens here near the end? Are we even seeing all the output? I think we are. Okay. We get to 5.8 while cheating. And where is our end? In this case, our end pause. Oh, this is a point. Oh, these are not the right. How did that happen? Um, yeah, yeah. End pause is an option of end, so it's not comparing against end. So that was a type safety error that we didn't have guarded against. Okay, so 180. How many cheats would save you at least 100 seconds? Oh, hold on, hold on. Um, right, that's a different question. So we don't want the minimum. Hmm. How many cheats save you at least 100 seconds? Okay, let's parameterize this with the start state. Um, yeah. And so we'll make a note, 180 fastest with cheating. But we want to know the actual cost. No cheat min cost. Oh, right. The racetrack is just going to be, yeah. Okay. It's just 180. Wait, 180 was the fastest cheating? That seems wrong. Oh, wait. Can't cheat. Um, cheated already. 9348, really? 9348. Okay, so how many save you at least 100 picoseconds? Is this path even 180 seems so low compared to that. Is that even possible? Or is that really? You find only the 64 cheat? Okay, I'm gonna go back to the example. So the fastest cheat, oh, I don't even find, okay, no, if you're not cheating, it's 84, right? Let's see if that's mentioned here. Okay, yeah, 84 seconds. But if you start with a can cheat, then 20, is there a 20-second route? Um, could complete in 20, 64, saving 20 seconds. Okay. 38 seconds. 84 minus 38, 46. I mean, okay, if this is true, so we can save 64 seconds. Oh, yeah, yeah. Okay, I have that one. So I trust this is working. I just need to get all of them. Um, let's see. Let's have a benchmark. So benchmark int, and if the cost is less than the benchmark and we hit the end position, we add it in. So val options equals set dot empty of distinct states, I suppose. Well, no, not states. We just want to count. Let's do var options equals 0. Okay, so while costs of visiting, wait, I should make this a separate method because I do want to keep this normal search handy. Count viable. So now we have a benchmark of our options equals 0. And our loop changes. Instead of visiting pauses and pause, we do while I suppose as long as the cost is still less than the benchmark. While, yeah, visiting should always have a cost. Cost of visiting was less than or equal to benchmark. Okay, so how many save at least 100 milliseconds? Okay. We don't need these print lines. And now, if visiting the position is end position, then options plus equals 1, of course. Yeah, makes sense. And in that case, we don't reintroduce this into the queue. So we just do options plus equals -1, and we put everything else in the else case. And then after all of that, we still dequeue a new visiting. Okay. So let's do it this way. No cheat cost is that start state, and val ends 1 equals count viable with can cheat and a benchmark of no cheat cost minus 100. Missing argument for parameter benchmark. Wait, search shouldn't have a benchmark, right? Okay, I'm writing entirely too much code to do this, but oh, we don't return the cost of visiting at the end. We just return the number of options. Okay. Well, I mean, in the first case, in the example case, nothing can save you. 64 is the most you can save. So let's change it to minus 64. We should get 1. Okay, and I don't know, 38. We should get 2. Um, and let's just say no cheat cost. So anything up until. Nope. Let's do minus 1. We are only counting 1. Okay, what's going on? Am I accidentally pruning things because of the cheat? No, the cost goes with the includes the cheating state. So I'm not accidentally pruning things because I found a better way there by cheating. So I don't have to worry about that. Um, let's just try this in the real problem. I want to see what number I'm getting. Probably still 1. Okay. And this count variable, I'm just going to put the start here. And in the search, we honestly don't need. You can include the start in both of these. Okay, slight refactor. Okay, so we're apparently only finding the best path. We're at 1479. Yes, this is a fun one. I thought I had it a sec ago, but apparently I'm only finding one option. Let's do a print. Wait, hold on. Let's just think about it for a sec. So we keep iterating the visiting, right, from our priority queue. If visiting ever hits the end position, we just add to our options, right? Otherwise, we keep searching down that path. Okay. And why would this only find the fastest cheat? I think this is happening. I'm only finding the 64-second cheat. I'm not finding the 38-second cheat. So a 64-second cheat gets there first. And then we keep searching. We keep searching because the cost of whatever we're visiting is still less than or equal to the benchmark, the non-cheating benchmark, right? Hellhound. Welcome, welcome. I was almost late tonight. I barely got in 5 minutes before. How's the problem going for you? Have you started? Okay. Why am I not finding further? I'll get myself a message when I do find an option. Whoops. Oh no, what's going on? Okay. So when we find it, we do that. Otherwise, we pop something else off and we keep printing our visiting state. Oh yeah, I should check the stupid list. Um, at the start of the stream tonight, I introduced the "Am I being stupid?" checklist. You can see it in my browser tab on the right. Yeah, am I being stupid or am I just stupid? When I don't sleep, I'm just stupid. Okay, so what's going on? Okay, so when we search here, at some point we find. Oh, I'm gonna want to print this in a Scratch. So we'll copy worksheet output. Oh, no, Scratch, and we'll find. Okay, so at this point we find something. Oh, I should have printed the costs too. And then we keep searching, and surely in all this searching, we find other stuff that hits the end position, right? Oh, wait. We are not. Maybe. I know what might be happening. So we do continue searching. Let's see. We prevent based on the cost key set here. So, if there's already a best end position here, we don't allow it, and we want to keep all of those. Yeah, so we're preventing and queuing that, which prevents it being dequeued at some point later. So we need to allow that. Cost.keyset minus the end state for end states. We want a set here. Immutable set of state. So we're going to diff it against the key set, which is itself diffed against end states. Okay, and when we find this, at this point, we add it to the end states. Well, hold on. No, those should include the cost. Okay, we still want to diff against that key set. Let's make this a little function that checks if its position is the end. Or you know what? We'll just define end states as a set. And pause again, cheating, and cheated. Okay, now if we diff this, now we should get multiple. And then once we hit that end state here, we won't enqueue anything from it, but we will enumerate it as an option. Yeah. Oh, frick. Okay, the cost map is wrong though, because those states are not unique anymore. So if visiting is at the end position, is one of the end states, then this check here doesn't make sense. Okay, how do we say this? I think I shouldn't have Dijkstra'd at all, actually. Um, so we check out the end states. Sure. I mean, it's a racetrack. I'm not really worried about branching. I could include the cost so far in the state, not just the cheating status. Or I could do something gross. So, we could say, um, visiting that pause is equal to end pause, and what else? So if it's the end position, then I don't care about this. So if it's the end position, then we are fine to continue. Um, well, okay. End states kind of need more uniqueness. Yeah, yesterday's would BFS too. BFS or DFS, and the day before as well. Um, I ended up rewriting this as a flood file with a binary search. I think that's pretty concise. I'm happy with it. Um, yeah, I should be doing a BFS here. My cost map doesn't work in this case with the. Yeah, this thing's not even a maze. I mean, I suppose it could be thought of like a maze. Well, but then we want all possible paths to the end. Um, in which case the cost doesn't even really help because we don't care about prioritizing that. I should just turn this into BFS. I shouldn't be using Dijkstra. Um, do I just start from scratch? Can I salvage this? Um, okay. I mean, we still want to check against the benchmark. You know what? We'll just have a new state here. Um, our priority queue includes the cost. That can also save this. Uh, and I guess we have a min cost, which depends on the state. If there is a min cost to get somewhere, then we're gonna stop searching. So we really don't even want that, do we? Yeah, so we just don't even diff. We just don't even diff by this. And we keep the cost with us. So our start should include a cost. We don't do that min cost. We're still gonna order by cost. So order by I don't know. We have a tuple here. Okay. Okay, so we're doing a tuple now. And these are end states. I don't know if that matters anymore. Sorry for calling it. What do you mean sorry for calling it? Did you call something bad? Um, oh, wait. We can just do ordering that by here. Underscore dot two. Okay, right. Okay. So while visiting underscore two. You know what? I'm gonna use a name tuple here. Just to mess around. Here's like a new well, no, it's an experimental feature. I'm not gonna do the imports. Okay, well the cost is less than or equal to benchmark. If the position was end position, we add it to our options, otherwise visiting for each, etc. Yada yada. Okay. Wait, not visiting that pause, but visiting that state that pause. Pause is not a member of int. What is visiting? Oh, wait. Underscore one. Here we go. Okay, and let me check the states. We don't care about costs anymore. And we shouldn't even use a priority queue. We should just use a regular queue, but whatever, it's already imported. Q.enqueue, the state to the cost, right? Yeah. Okay, well, now it's running. Yeah, I think I jumped right down to the Dijkstra because I read this. I saw a maze in my head, not a racetrack. Yeah, there's only one path through. You should always go closer. So okay, now we're timing out. So now that tells me that we have too many states. We could order by the cost, right? But we're gonna end up like looping around. Yes. So we're gonna loop backwards is the problem here. We do still need to dedupe states. Okay, deduping states. So that's the heart of what makes this problem tricky. Okay. So we need to dedupe states, but we have to be careful when we're deduping states that we don't remove something. So I suppose maybe we have to find a path, and next should only go forward along the path. Yeah. So because there's a racetrack, there's always a clear way forward. So that'll prevent us from looping. But now when we cheat across a wall, how do we know which way is forward? Yeah, we just have to generate the path. We can't just look left and right and go. Okay, so we generate the path. And our next function, when we cheat, we can skip the path, but otherwise we stick on the path. And that prevents us from looping. Right? And we can't simply avoid a path that has a cheaper cost because that path might have come from a. Oh, wait. Okay, I have a new idea. So we can do it with this cheating state. I have a way to dedupe states. So cheated should include the time at which they cheated. Yes. So, yeah. So case cheat. Oh, no, not here. So you can cheat in different ways. So we have case can cheat, case cheating. I solved it. And then and int. Okay, this allows us to dedupe our cheating states or tell them apart, and then we can just go back to the Dijkstra-ish solution, right? Because that makes them unique. The time at which they cheat, unless the precision at which they cheat is also important. So yeah, time and position. Time and position point. Okay. Okay. We can dedupe. Yeah. I'm just gonna delete this copy search function here, which is just Dijkstra. And we will use Dijkstra now that we can dedupe properly. Okay, so start is can cheat. And while visiting pos equals end pos, that changes to while cost of visiting is less than or equal to our what do we call it? Benchmark threshold. Fair enough. Wait, you didn't tell us if you're done or not. I mean, you are done. You don't get stuck here. Okay, so while cost of visiting is less than or equal to benchmark. Sure. And now we can do this diff cost at key set because a key set is the states and the states are differentiated. But now when we do next, we do need parameters. I guess cheating will contain time and position as well. So next needs time and position as a parameter. So when we go to cheating, we have a time and pause, and when we go to cheated, we also have a time and position. Okay, cheating next. So cheating that next. And we have our current position and time. So we need to pass time as a parameter here, which means we need it here next. And then cheating next. needs that time. Sheet.next with the time and position. There we go. What else are we missing? Surely there's a compilation error here because we have visiting.next. Okay, and then we add the cost of visiting as the time parameter. Okay, yeah, all the cheats are unique, right? So all the states that have cheated are unique. Meanwhile, the state that doesn't cheat all get deduped against themselves. We won't have an infinite loop. So our states are sufficiently deduped. Now my question is, why is my worksheet not running? Oh wait, we don't want to return the cost of visiting here. Oh, we have search defined twice. We have count cheats. Okay, and what we return here is, oh, we need a cheat count still. So bar cheat count starts at 0. And if visiting dot position is end position, then we do cheat count. Otherwise, we use this position, which is not an end, to continue the search. Okay. Surely there are compilation errors here. I don't know why I'm not hearing anything. Thread death. I'm just gonna restart the server. I should really talk to the mouse is unresponsive. Okay, thank you. Yeesh. I really love the idea behind the worksheets, but I do run into weird performance issues. And I feel like I'm perhaps a particularly heavy user of them, so it's probably on me to go to the maintainers with my issues. And I have gone to them before. Like there's a bug I reported once where if you had the worksheet open in 2 different windows, then it would run it twice instead of just once. So I got that one taken care of. But apparently there are more bugs to report, and I'm not sure I even understand what happens. Count variable doesn't exist. How are you evaluating a worksheet? Okay, it doesn't even compile. Count sheets, no cheat cost minus, yeah. Visiting.diff. Oh, this also needs cost of visiting added to the state. There we go. Okay. Wait, found unit required an int. Oh, right, we haven't returned anything yet. So we returned the cheat count. Okay, I think now we're compiling, and I'm pretty confident in this solution. Oh, cheated. Let's say we cheated at that. 0 and start pause, sure. We have a match error happening. When exactly? Oh, here. Right. So Under cheating, we have time and precision. We don't care about those. Okay, we're getting there. Match error, cheating. Okay, inside next, line 22. Oh, cheated. We can't do next when we've already cheated. Okay, so I suspect that's happening because... Oh, here we go. Definitely a day you cannot solve without Claude. Part 1, yes. Part 2, no. Learning about your limits, huh? So, part 2 is a tough one. I hope I have a good framework in place for part 2. Okay, so now we're back to taking too long. Let's try this on the example and see what happens. And maybe we need to diff more aggressively. Of course, if it's minus 100, that's going to be 0. But let's do minus 1. Anything that's faster at all. Oh, there are 118 ways to save 1 second. Didn't really give us 14 cheats to save 2 seconds. What's the sum of... I want a sum of these for my test. Okay, there's 1, 2, 3, 4, 5 cheats that save at least 20. So let's do 20 here. We should get 5. Game over for this morning. Ah, yes, it's been an hour in. This is not that far from previous days. I'm not saying which approach I took right now, but both part 1 and part 2 are not happening for the first time this season. Not that far from competitive programming core. Okay. Part 2 is confusing. Oh, I'm not going to read that. That sounds spoilery. We'll get to it. All right. See you tomorrow. Have a good one. Have a good one. Okay. So apparently we have 12 cheats. So we're counting too many. We're not we're back to not deduping enough, which explains also why yeah, why it runs too long on part 2 or on the real answer. Real input. There's a threshold right here. How many save 64 picoseconds? So we say 3 save 64 picoseconds. Let's print those dates. Yeah, we'll print those. So we cheated at 18, 19, or 1877 at 5-7. So those 3 are considered distinct, even though they all start the same place and go in different directions. Where is 5-7 in this example? So 1, 2, 3. Let me blow that up a bit. All right. So 1, 2, 3, 4, 5. wait. No. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay. So here is where we cheated. The cost was 64 less than. And what is the difference between those three states? So we are cheated at 5, 7, but at different times, 18, 19, and 18. Maybe we should just keep track of where the cheat started. So the state is at 0.57, but we cheated. I also want to know the time. So we had the state. I want to know also the cost. Visiting or cost of visiting and visiting. Okay, so these all have a cost of 20, stands to reason, and 5, 7. And in one, we have a cheated at 19 from where? Oh, geez. To keep that hover up. From 6, 7 to the right. And we have one cheated from 6, 6, diagonal upright at 18 seconds. How are we getting from there? Okay, let's recheck our cheating code here. I think I do want to just do the time when they first cheated. So when we were cheating, yeah, when we're cheating, we just pass that along. And then we can figure out the rest from there, right? And then now going into a cheating state. So next, so if we are at a can cheat state, position, time, we'll pass that time along. Oh, wait, it's time and position. And when we're in a cheated state, then we can only do a non-cheating next move. And the cheating next method, we pass the current time and place. Yeah. So this is the point before they are clipping where they started the cheat. Okay, let's take a look at that. Oh, now we have two states. Okay, this is an improvement. So they both get to 5, 7 in 20 seconds. One started cheating 3 seconds beforehand. Ooh, that shouldn't work. So one started cheating 3 seconds beforehand at 7, 6. Oh, if they are currently on the wall, I suppose. If they are currently on the wall, it should not be possible to move when you're not cheating. Okay, so my clip kind of lasts too long then. Let's think about what happens. Here, Okay, when we are here, we are at a non-cheating state. I'm just gonna print. I'm gonna print. Well, hold on. At 17 and at 7.6. Okay, so we're at this dot here, 17 seconds in. And then we decide to cheat. So I suppose we're moving here, right? 18. And now our state is currently cheating. Okay, so I guess when your state is currently cheating, you shouldn't be able to clip again. Well, you can clip for 2 seconds. 1, 2, 3, right? Am I misunderstanding this? 1, 2, 3. That's clipping for 2 seconds. Up to 2 pixels. Okay, I think I'm just misunderstanding that. So when we are currently cheating, it has to be non-cheating next, I guess. Non-cheating next. Yeah, I guess, yeah, you can't clip through walls that are too thick. Okay. Okay. Minus 64, minus 40 should give us 2. No, that's no good. Not minus 40. Yeah, okay, let's do minus 20. This should get us 5, right? Because our threshold is much higher there. Okay, so now we are missing some cheats. We do have the 20-second run, which saves 64 seconds. Yeah. 46-second run. And now I guess our cheats aren't going far enough, deep enough. Okay, which cheat states are missing here? Well, let's at least check performance here. I just wanna know ballpark. Will this work? Oh, I don't want 20, I want 100. Cancel that. I don't want that many states. Okay. We'll let that run again to make sure it's gonna be performant enough. In the meantime, let's look at this hover. 20, 46, and 48 is the times. So what is it, 84 minus each of those? So 84 minus 20 is our 64. We have our 64-second run. We have our 38-second run. And we have our 36-second run. So we're missing the 20 and the 40-second runs. Let's take a look at the 40-second run. They don't show us where the 40-second run is. No. Okay, let me try to understand the clipping a little bit more. So cheating for 2 seconds means you can only skip one block, right? That's what it means. And I think that's what I was misunderstanding. Allowed to cheat. Disable collisions for up to 2 seconds. Yeah, I mean, I just don't know how, going left, then down, then left isn't considered a 2-second cheat, right? There are 2 ways to get to 64. You can cheat by clipping through the corner here, going down and going left, or corner, going left more and then going down, right? Clipping through both of these should be considered a 2-second. So I take issue with the wording here. 1, 2, yeah. Save. Complete the course in 64 seconds, saving 20 seconds by doing 1, 2 here. We are somehow missing that one now. Okay, let's go what we have. I should print what it saves. Oh, I'm not listening to myself. Okay. Let's take a look at our cheating behavior. If we can cheat, sure, we just pass along our time. And okay, so cheating next. We take that time that's passed along. We pass along our current position. I think cheating next should also include the position. So time and position. And in fact, well, yeah. So time and position. Oh, but these are both non-cheating nexts now. Okay, I'm moving on the assumption that you can't cheat through a too thick wall. That doesn't matter here because there aren't any of those, so that's not actually causing an issue. So I think that's a fair assumption for now. But if that gets me later, I'll be upset with Eric. So case the current state, time and position that we first started cheating. We say we cheated and we keep a record of that time and position when we first started cheating. I mean, that seems fine. That seems fine. Okay, since this does it in terms of how much time you save, let's move back to the example. I want to turn more than just the cheat count. Let's do find cheats, and we want to return a set cheats. So a cheat being, I guess, an end state. So yeah, just an end state where we cheated. Okay. So for our cheats, it's going to be an empty set. Set.empty state. Immutable set, empty state. Instead of adding to the cheat count, we are simply going to add to cheats. plus equals visiting a current state. Okay. And then we just return cheats. And let's change this threshold back down to 20. Okay, and well, now that we have those states, so count sheets, this is going to be find sheets. And I want to do some printing here. So find sheets. Sheets, not for each. And let's make a list. So we can just have these printed. So print line, what do we do with an L? We want to print the state, but we want to print oh, we should include the cost of what we return. So cheats plus equals visiting, and then the cost of visiting. Okay. So this returns a state to an int. I'm low on time tonight, so it's likely I'll just do part 1 and then show up early tomorrow night to finish part 2. This doesn't need to be set. It could be a list, but I've already done it that way. Okay. Now, I'll show. Just gonna have our state and our time. And what we want to print is the time saved. Yeah, so we'll do no cheat cost minus t. To get the time saved, and then you just show the state. And we'll just do this manually for the first 3. Okay, let that run. Geez, I just spent time doing that so I could write some debug code. I don't know why this would be running for a long time. I haven't changed anything substantial to the algorithm. This was running instantly a second ago. Oh. That's a nonsense error. Importing build. Oh, that's weird. Okay, we restart VS Code. Maybe after I kill all Java. Alrighty, let VS Code boot up while we think about this. So we are missing this cheat and this cheat, I believe. Surely the 47 one, which they didn't specify where that is, unfortunately. But we could at least verify the others against this, right? The 38-second saving and the 20-second saving. And I could reflect on like other approaches I could have taken. So instead of making, cheating part of the state, so my state is not just position, but whether we can still cheat, and when we've cheated, the time and place where we decide to cheat. Oh, thank you. Thank you. I'm glad I'm sharing it well. That's part of the reason I started streaming, honestly. I used to speak at conferences, and I don't think I was a very good speaker. So I thought, okay, this is at least some sort of practice to do that kind of a thing and try to share my thoughts more clearly. And when you're whiteboarding at work or pair programming, I think it's helpful to be able to share your thoughts as you go. So I'm glad you're liking that because it's an intentional reason to stream. Okay, so the one where we save 64 seconds, we cheated at 5.7 right here. Okay, the one where we save 38 seconds, we cheated 19 seconds in at 8.7. So 5. Wait, so this one we cheated 18 seconds in, 19 seconds in right here at 8.7. Okay. And we assume that means we went south. I should record the wall instead. So maybe I should update that so that we know which wall is being passed and at what time that wall is being passed. But we can figure out based on context. So it found that. And the 36-second, which I don't think is mentioned here, but I want to know when that happens. So at 20, 30 seconds. So 20 would be here, the next step, 18, 19, 20. We're probably skipping this wall. And that saves us 36 seconds. Wait, does that even make sense? Didn't they show that wall? Yeah, they showed this wall. Oh, right. I see what's going on here. We go south. So to save 36 seconds, we follow the wall a little bit longer before deciding to cheat right here instead. And that's why it's 2 longer. Okay. But now apparently we're failing to find this cheat. Oh, right. Because we dedupe from where the cheat starts, we're not considering the direction. Yeah, we're not considering the direction. Okay, so this is an argument for making it the wall that is cheated upon. So the wall and the time, because at some point you might have multiple walls to choose from. Okay, so this debugging helped. let's change this up. So currently cheating, I don't think needs a time and position, because if we're currently cheating, we don't want to be deduping that. So let's change that in our model. And now we have our next. Yeah, it's just not even in there. So time and position now comes not from the previous, not from the cheating state, but from what's happening right now. And that's what will be recorded, because cheating is when we're on the wall. Right? So we still temporarily have this. Oh, no. We don't have this. So we just change from can cheat to cheating, and only the cheated states get deduped. Yeah, now we don't care about this. And non-cheating next will always take our current time and position, or our cheating next. Okay. Now let's give that a shot. Now we're erring because now we're only finding one. Oh, right. Because we are now deduping these. We're now deduping these cheating states. We do still want to. Well, hold on. What exactly is happening there? So we're only finding one. And we're in fact finding the best one. So we are deduping the cheated states. Oh, and why is the final state cheating rather than... This is a point at which they were cheating. What state is being passed along? So it says they were cheating at 5-7. This is 5-7 here, isn't it? I want that to have the walls location. So I've messed up there. But it's still weird to me. So the can cheats will get deduped because of the min cost, and so will the cheatings, right? If you can cheat somewhere else with min cost. So okay. So we do need a time and position in cheating, but we need to be able to branch from there in multiple directions. I mean, sure. So even if the time and pause is there, right? Like these two in this corner, we're the same time and position. So even though we're going south and right, it's just that we need to make sure we get both of the possible cheats from there. And because our cheated state was keeping this original location, then both of those got deduped. So we just need to make sure that the cheated that the states where they're on the block are deduping. Okay, so we think carefully about this. I think we'll look at this from the top down. So in our state, we're trying to get our next. So our non-cheating next is very straightforward, just the normal approach. Okay, cheating next can happen. Only it can cheat. Okay. So this here will be the time and position when we were originally cheating. And then cheating next, we pass along that time and position when we call cheat.next. And cheat.next, we should record that time and position, right? So in the case of the corner here, we should have a cheating state here and a cheating state here with the same time but different positions. Oh, hold up. What we pass along there when we call cheating next is a current time and the current position. Um, so in cheating next here, we need to pass along the new position. Yes, we need to pass along the new position. Um, so the new position goes here. We also want a new position here in the record of cheat.next. And what is the time that we are passing along? It's when we call next, and it's the cost of visiting. So it is a time at our current state before walking. So I suppose we do a +1 there. Yeah, that's one way to do it. We could do a +1 here or down lower below. I think just to be consistent with the fact that we're doing a new pause here, we'll also do time +1. We don't need pause as an argument because it's going to be our current position. So we just need the time. The time when we decide to cheat. And then this records the time when we are cheating. Okay. Okay, this is feeling better. And then this does a non-cheating next. Okay. We do next with a new position and the time. This could be the time at which, so, hmm. So cheating now will have parameters here. I think I still want to record the time when we were cheating. So time, position, and we'll keep that time and position shadowing these. So the cheated will still show the time when we were on the block, right? Will that come back to bite us? Let's say there's two ways to get to the same position. But yeah, they should be distinct by their cheating time. So we maintain that when we do cheated. So this time is really only for this is the block time. And I can redesign this so that's more clear, but I think if we at least have something that should work. Unset local variable. Oh, yes. Um, okay. So now, what's the size of this? Yep. We're getting it. L dot size. Yeah, we're finally getting it. Cool. Those are all of our states. Let's do L dot for yeah, L for each show. 64, 20, 36, 38, 40. Lovely. And let's see that we can still do. So we should add 3 more when we have 12 picoseconds, or when we save 12 picoseconds. And now the size is 8. Excellent. These three. So we all got to 5.7, but we cheat at 45, 13, and 23 on these three blocks. Okay, so that's the block we clipped through. Alrighty. Well, let's change that back. And let's run this on a main problem. Am I still going to have performance issues? So, okay, so we use a priority queue. And we are deduping all the non-cheating positions. So we shouldn't be running back in circles on any of them. Like every time we cheat, we make a new branch in our states. So this cost map should only have like so many per state. Like per or per cheat, it's deduping by min cost. But we failed to evaluate the worksheet. 30 seconds. Okay. It still needs to be faster. Still needs to be faster. We could go back to returning the count. Yeah. And we are deduping those by using the cost key set, so I'm not worried. And we're gonna turn gcount. Okay, so we'll just comment that code. In fact, we'll comment the old method signature as well. So this is just returning an int. Okay. Oh, we still need that. Let's do a much greater threshold. Oh, wait, we were getting an empty set? Were we getting an empty set? No, that was for when we were doing it with the example problem. Oh, we got an indent error. What do you mean? What are these errors? Are those from indentation? Okay. I'm just gonna let this run this way, make sure everything else still works. I'm gonna do a greater threshold and see if part of my performance issue disappears, and then we'll do some print line debugging to try and figure out whether or not we're deduping enough. Because if it's a performance issue, that's number one candidate, right? Is that we're not pruning. Like, how are you reaching a timeout? We're reaching a timeout on the search, on the normal search? I mean, it starts with cheated 0. So this cost should basically dedupe based on position, right? So you have a min cost per position. because the cheat state really doesn't exist. Okay. Yeah, we are failing on this basic part, which we weren't failing on earlier. We're failing to run just a normal. Admittedly, like this is a Dijkstra when a BFS will do, but still, this was running just fine earlier. So that's curious. Why would my normal search have become? I mean, honestly, it's not even really a like BFS, DFS. It's all the same thing here because there's only one way to go. Like we could change this. It's still. I would. I do want to change this, but I want to understand why the performance is off because that can help understand. That can help me understand why the performance of this next one would be off, right? Um, so when we call next, right? Our state.next will always have had cheated. So we just go to non-cheating next. And this is very straightforward. Oh, okay, wait, there's a difference here. Oh no, they're both basically using a new position. Um, but now this is also including the new cheat, which is made from the new time as well as a new position. Um, wait, I didn't touch anything here. I didn't touch anything here. So I touched things here. But even then, this wasn't really used, right? So I don't understand why this search norm no longer works. Um, I think maybe we stop using that. We'll stop using that, and we can very quickly just search the normal path. Um, I just want to make sure my worksheet's still up. Nothing is running right now, so this should be able to calculate 2 plus 2, right? Yeah, it's not running any calculations. I think perhaps. Yeah, this issue of the worksheets where when you run them too hard, you get the whole thing just dies. Like what it should be doing is stopping evaluation when it runs too long, but apparently just had the whole thread die out of memory error. Hmm. Okay, restart the server, see if that helps here. Yeah, it's unresponsive. I'm painfully aware that mouse is unresponsive. I can also, in the meantime, just convert this to a normal Scala file. Okay, we'll keep the worksheet on the right in case it decides to wake up. And we'll just make a normal Scala file, and we'll run things in the console. So d20.scala def, well, hold on, we need a package. Package y2020 def d20. Okay. And all this stuff we can just indent. Okay, so we'll print the no cheat cost. Yeah, for now, we'll just do that. And we run that in SBT. Well, luckily I can close VS Code and SBT will still be happy. Okay. Just gotta compile. That doesn't matter. Day 20. Oh, okay. SBT does care about forward references. Okay, pause adjacent walls. Walls. Right. Okay. How's part 2? Great question. I'm just doing part 1 tonight. I'm gonna go to sleep. I'm having a performance issue, I think. I think I'm having a performance issue in part 1, but I'm not sure because my worksheets are just kind of dead. I don't think I should have a performance issue. Okay, we have an issue with find sheets. It's unused. Sure. It doesn't matter. Okay. So I'm compiling my code and running it normally because I'm struggling with the worksheets. Uh, Where is my, oh, wait, we forgot to main def this at main. Okay. And I can just do 0 y 2024 dot d20. Okay, I mean, look, that runs instantly. If this runs instantly, why does my worksheet not run it? Right? Do I have to be done with worksheets? Okay, well, I mean, if that works there, then let's just try getting the answer. So print line as 1. And we run it again. See, worksheets are supposed to be time saving. Okay, it is taking a hot second, which, you know, I do believe that. Which makes me want to look at my state deduping. So my tree pruning here. You asked, how am I checking for cheat? So what I've done here is my state includes whether I can cheat, and if I've cheated, the time and position at which I cheated. So this is a Dijkstra, but my state, like my min cost, includes the time and position where we cheated. So that means for every cheat, for every wall clip, we are only keeping the min cost for each possible position, right? Um, but okay, yes, the GC is thrashing, so we do have too many states. That's pretty straightforward. I'll try to debug that, but in the meantime, like I'm here, I'm tired. We're just gonna run SBT with a lot of memory and let it go. So SBT dash mem. Hold on, I forget. I have it aliased. Okay. I'll let you see what I'm doing here. So we're gonna do SBT dash mem 2 gigs. Let's do 32 gigs. Let's do 64 gigs. Why not? No, that's ridiculous. Okay, we'll just let that run. Yes, I've considered doing it other ways. I already have this, and I think it should work fine. Um, like one way I think would be elegant to do this. Is simply to turn so our maze here's not a maze. There's just like one path, but turn that into one-way nodes where your time increases. Your time increases by 2 when you cross over a wall. But yeah, definitely like a few different approaches you could take. But I think this should work, and I do like having this kind of state machine happening. So I want to make this state thing work out. But just so you could see, we have our cheating state, and then we have a way to progress that state. So we go from can cheating to currently cheating to cheated, and cheated records the time and place where that cheat happened, right? And then our state is this is just a normal this is a normal Dijkstra. This isn't even really Dijkstra. This is a normal BFS adjacent. And we only try this cheating version where we change our cheat state when we had the ability to cheat. So when we can cheat, we do that. And this works fine on the example. So I think the logic is fine. Oh, I think I want to print some states so I could know what's overly duplicated. So let me think about how I'm deduplicating. Sure. Um, I mean, I'm still sticking with it because I like the idea. Right. I mean, the idea originally was just an enum of 3, and where you normally search with precision, you just have a precision plus an enum, and you search for that. Um, okay. So while it costs this logic is fine. My problem here is in deduping. So we take our next, passing along our time, and then we diff from our cost key set. And diffing from the cost key set, start to 0. If I get Dijkstra to work, then that's, yeah, I mean, Dijkstra, not super necessary here. I started with it because I thought we had a maze to start. I mean, even then, like, the cost isn't really. Hmm. Well, actually, I guess Dijkstra does make sense because the cost isn't exactly uniform, right? Because the cost can be much slower to move into somewhere. And I could very easily change this to an A star, but I don't think that's my main issue. Okay, so when our visiting is not at the next position, right, then we look for, or when our visiting is not the end position, then we look for next positions, and we diff out things that already have a cheaper cost. And this diff only works correctly because of the cheat enum. And let me think about how that cheat enum helps here. So if we place in a bunch of cheat, there will be, let's go back to an example here. So I like using this corner here because from here we can cheat in 2 different directions. So we're going to have this in our min cost, right? There's going to be a min cost to get here without cheating. And then we get all the next positions, which some of the next positions, so there's going to be a non-cheating position, there's going to be a currently cheating position, and another currently cheating position. So each of those are going to have their own associated min cost, given that they are cheating at that time. Yeah. Now it could be. Okay, I do have an idea, but first let me just work through this logic. So after we get the cheating, then we get here a state here that says cheated, but I cheated at this time and place, right? And we get a state here that says cheated, but I cheated at this time and place. And that will have its own min cost. Now, a potential issue that I just thought of is perhaps we start going backwards, right? And for this branch where we start this cheating, and again, we're like searching all branches by like the lowest cost first. But now we have 2 branches come out from here. And the one that goes backwards might go backwards for a while. Once it gets to the S, it's not going to have any other options. So that branch should be kind of dead. But it does have to backtrack all the way to the S, and it does have to search for the end. But that's not a big deal. That's like an n over 2, roughly over 2 optimization to choose just one path instead of the other. Okay, so we have this cheated state, we have this cheated state. So for every time when we can cheat, but if we look at our input, maybe there are like way too many. There are a lot of times and places to cheat. Yeah. So in this version, there are lots of times and places to cheat. And that alone can be the reason why. Let's say, for example, that we can cheat by crossing this wall and going over to the right. Then all these cheats here will be distinct. So they'll all have their distinct search branching off. Okay, yeah, I see where my issue is. They all have their distinct states branching off, even though they're essentially doing the same thing and will have the same time. So perhaps what I should do. Oh, okay. What I should do is just get the map of like all the costs, right? There's a cost to get to here. I should take advantage of the fact that this is not a maze. So since this is not a maze, each of these has a number, right? Then we can cross over the wall and check that number and subtract. We could subtract them. Yeah, so check for each point essentially. Uh, yeah, I mean, I did kind of say much earlier tonight I shouldn't be using a Dijkstra here. I never really drilled down on that thought. Yeah, yeah. Okay. That's why there's too many. There's just too many ways to cheat. Alrighty, alrighty. This is very easy to implement. Um, we'll keep this day20.scala as a record of what my first approach was. But I think I will kind of start fresh in my worksheet here. Yeah, so our first round through will generate like a heat map, getting to the end. And then we'll just use that heat map. Uh, I kind of really liked this, but whatever. In a different problem, this enum would make a lot of sense to just add more state to your add an enum to your state. Hmm. Um. Okay, so let's restart the timer. Let's restart the timer. We had a little 2 hour. I think part of it is like I misunderstood the problem. I thought it was like a maze search. I started by writing a Dijkstra to search the maze. And then I realized, oh, it's a count. It's not just searching for the fastest. So the Dijkstra actually makes sense if you're searching for just the fastest. If you're searching, you know, all of them, then that's a little bit different. So def map, or I mean, I guess it could be a val. Map point to the int. Cool. So no. We'll just do a flood fill from the start. We implemented a flood fill 2 days ago. We'll just use that. Okay. Okay. We have an iterator set of points. We can just pass in walls as are blocked. And we need to have like an end state. Okay, so we flood fill starting from, oh, I guess it just starts from start, pause. Okay. Okay, so we flood fill. We want a heat map, so val heat map from int point, no, point to int. So flip fill with the walls. Dot take while. Oh, hold on. We have the end. We'll take while non-empty. Take while non-empty. Okay, and that just walks through all the way to the end. The last set. These are returning sets. Each set should have only 1 point. So we're gonna map each of these sets. We're just gonna take that head. Nope. We're gonna make sure it's not empty first. Okay. Okay, this one feels kind of too much. It's more than I need. I'll rewrite that as a refactor when we're done. Don't need branching. Okay, we flat map adjacent, diff against the previous, diff blocked, and then filter inbounds. Okay, that makes sense. So we get the head. And then we're gonna zip with index. And once we've done that, we just turn it to a map. And we can test that out with heat map end pause. That should be the cost of moving all the way through a map, and heat map start pause should be 0. Okay, 09348. Cool. And then we want possible cheats. So basically, I guess for every internal wall, how do we search this? Okay, so for every internal wall, we consider taking down that wall. This has a distance to the end. Or no, this has a cost to get there. That's going to be 0. This also has a cost to get there, but we can subtract the end from that. So like cost to get to the end minus this. Okay, so we'll cheat for points. So def cheat at a point, and I want the cost. Let's go to the test because I have a specific example I want to test on. Okay, and now the wall should have 2 that are nearby. So val path points. And not every wall can be a cheat, so I'm going to make that an option. So we're going to take adjacent, and we're going to filter, yeah, area contains filter not walls, sure. Just our usual next function. And when the size is 2, well, okay, here's one where it can be 3. But any scenario like this, I don't think we have like any diagonal stuff going on, right? Yeah, I'm gonna go into assumption we don't have any diagonal stuff going on. So anytime we have 3, we can just ignore that. Because it's not like it helps with 3 at most. That'd not be the case if you know, you had walls here and here. We'll make a note here. Note, assuming no diagonal walls. Okay, so option dot when path points dot size equals 2. Um, so we take the lower cost and the higher cost. So we'll call them A and B, but I want to uh, sort by heat map exactly. Mm, So now we take heat map of end and pause minus heat map B. Hold on. Yeah, minus this cost going around here, plus the cost to start. So plus heat map of A. Um, to list here. Okay, now let's do cheat from start position dot right. And the cost, so the cost normally going from the start position, or the normal cost is 84. So by clipping across this wall, we save 6 seconds. 1, 2, 3, 4, 5, 6. Wait, no, that's not exactly true. We want +2, right? +2. Okay. So we can take all wall points. Well, we'll call them inner wall points. Inner wall points. Um, so we'll take walls dot filter area dot expand by -1 contains. And we have to keep in mind that this is a set. We don't want to accidentally set that map. Um, yeah, each of those walls is a unique cheat. So inner wall points dot to list. I was just going to list it here. Dot flat map with cheat. And let's do a count where the new cost is greater than or equal to heat map, and we should just give this a name. Val, what is this? Normal time? Yeah. So less than, greater than or equal to normal time minus 20. Oh, wait. Less than or equal to. Um, no. We want in between stuff. So let's say normal time minus 20 or minus 64. Minus 64. So it's the range of times you want to get to normal time minus 20. So this should count 5. go this range contains. Okay, that's 5. Great. So our ends one, now ends one is going to be save at least 100. So it works if you have time. What is time is less than or equal to normal time minus 100. Okay. So we count times for which normal time. Yeah, okay. And we have to switch to the normal problem input. Okay, well, I mean, that didn't take too long. 1321. That was super easy. um, okay, so let's read part 2, and I'm going to decide whether to do that or not. Apparently, a 2 picosecond cheating rule is deprecated. The latest version of cheating will permit a single cheat that instead lasts at most 20 picoseconds. Okay, I think we can handle this easily by looking at all points within like a distance. In addition to all the cheats that were possible in just 2 picoseconds, many more cheats are possible. Okay, because this but I hope we're not like I hope we're not asking the same question, because then now we have many different ways to go through this block wall, right? And I don't want to be counting all of those. I mean, I can do it with math. I definitely don't want to iterate over all of those. Because this cheat has the same start and end positions as the one above, it's the same cheat, even though the path taken during the cheat is different. But this is considered to be the same cheat. Okay, well, that's good. Okay. Cheats don't need to use all 20 picoseconds. Cheats can last any amount of time, up to and including 20 picoseconds. Any cheat time not used is lost. Okay. You still need a list of best cheats, but now there are even more to choose between. Here are more quantities of cheats in this example. Let's see. Okay, there are 32 cheats that save 50 picoseconds. Okay, so the start and end position of the cheat basically just go to another point within a range. We do want to count like this and this, cheating to 6 and cheating to like 7 here is separate, right? We do want to count that cheating to 7. I think so. I think so. Okay, well, I mean, I have a solution to it. I gotta think about the performance. So here, for cheat 2, we just gave ourselves what that point would be by looking at adjacent and choosing a wall to tear down. But what we could do is choose points up to any distance away. And then now we have a list of cheats. Yeah. I feel like I do want to prune those a bit. Well, we look at how much they save. Yeah, okay, we can do this. Let's give it a shot. So cheat 2 just gives us a list of int. Um, so A is just going to be the point, and B is going to be any point on the heat map a certain distance away. Yeah, any point on the heat map a certain distance away that is also cheaper, like further along, has higher heat. Um, val B points. Okay, how do we iterate these? We could just do 20 by 20 area around. So we could do an area around our point, expand it how many times? So for 2 area around our point, we expanded. Oh, we do have to count the number of blocks we are hitting. Okay, we have to count the number of blocks we are hitting. We can't just teleport. So if 2 millisecond net picoseconds means you can skip 1 block. So we have to do like a quick search if there is a path from. I wonder if going back to the Dijkstra approach here could make sense. Because now we know to search only for, right, like keep track of, I don't want to keep track of individual cheating states. There are just too many of them. Okay. Maybe not so straightforward right off the bat. But this is good because I do want to sleep. So I will sleep on that. And tomorrow I'll start at 11. I think if I've thought about this problem before I start a stream, usually those streams where I decide to like do it the next day are very fast. So I'll start tomorrow at 11 and we'll do a very fast implementation part 2. I don't know what I want to do. But yeah, I get a fun problem to sleep on. Okay, okay. Well, thanks for sticking around. Oh man, y'all let me go down that extra for a while. But you know what? It was still fun. I really like thinking about that model. Right? Like it is too many states, but it is a way you can model this kind of thing. And it was still fun exploration. Hail 21, thank you for the follow. I appreciate it. By the way, for people who are new here, I do have a leaderboard. So very welcome to join and push me down further in the ranks. Nope, that's a leaderboard I'm waiting. How are we doing today? I'm still holding 8, despite of not having finished yet. I think a lot of people will not have finished today. We get a fun weekend of hard problems. Oh, it'll be so nice to do this on the weekend. Having sleep and all that, you know? Um, yeah, who finished? arrow bounce, finish in 45 minutes, 23-minute delta. I should be able to think about a solution in 23 minutes. There's something about, there's something about being on the spot that makes you forget to like take a step back and think. There have been a couple times this season where stepping back and thinking was a solution that made me realize, oh, I can solve this in 5 minutes. You did brute force for part 2. 3 minutes. I don't want to have something take 3 minutes. I want all my worksheets. I want everything to be able to run in a worksheet, which I have a time limit set for 30 seconds. Okay. And me all the way at rank 20 today. Jeez. All right. Well, let's find someone to raid. Oh, I didn't use my Am I Being Stupid list. So I made an Am I Being Stupid list. Just like reflecting on past examples where I have spent time because of something stupid. Like this has got me surprisingly. I'm like debugging a solution and it's not just the input's not even correct. Because like I forgot to change when I did the copy paste. That feels such a waste of time. Okay, I had a little bit of this going on today. I did work on the example. What I didn't do today was consider why really it's taking so long. Like I kept considering that why my Dijkstra was long, or why my Dijkstra might be wrong. My Dijkstra was correct, but I didn't consider that. And did I discard a good idea? I don't think I mentioned a good idea earlier on. I did say I shouldn't even be using Dijkstra, so maybe in a sense I did that. Okay, well, so Twitch, advent of code, find someone to raid. And hey, let's. Oh, I might raid Whimsically Made. So this is. Do you all know APL, the array programming language? So this guy here does everything in BQN, which is like a modern APL that's supposed to be like more user friendly. But it's wild to watch. It's like a completely different way to think of this. I mean, it's still it makes heavy use of ligatures, so you have to ask what these ligatures mean. But other than that, like it's still fun to just watch him doing something so foreign, you know? So let's raid Whimsically Made. Ah, Fizzbuzz, thanks. I'm glad you like my list. You got the namespace collision one today? Yeah. Yeah, I'm gonna start using the list. And y'all need to remind me that I have an Am I Being Stupid list. Raid Whimsically Made. All right. Well, thank you all for sticking around. Fizzbuzz, Michael, Brett, Hellhound. Good to have all your input. And Michael, you're right about me over engineering. You're right. But the engineering part was fun. All right. Have a good night.